So I'm going to be talking about work we've been doing on building knowledge graphs. So my general area is not so much life sciences, but more on just the general technology for building knowledge graphs. So I started this title from developing new drugs to looking at critical minerals. Though I'm not really going to say much about new drugs, which I think is a good thing, since after I saw the last talk, I'm thinking, well, they know a lot more about finding new drugs than I do. So, but I am going to talk quite a bit more about critical minerals as sort of a motivating application. But I think all the techniques that we develop and the problems that we work on in terms of creating knowledge graphs apply across domains. So I tend to work on lots of different problems. I have worked on with Andrea, we worked on a project with Novartis on doing basically finding new drugs. So, all right, let's see. I have this clicker here, so I can get started. All right. So here's the outline for my talk. I'll start first what the problem is, sort of the general problems in terms of creating knowledge graphs, and I'll just touch on a couple different applications and use the second one here to motivate the rest of my talk. Then I'll just go through sort of the usual steps in terms of building knowledge graphs and talk about how we solve these particular problems in the work that we're doing. So, representing the domain, extracting data from papers and reports, which is often an important part of the problem, ingesting data from tables, since oftentimes there's lots of information in table information that we need to bring into the knowledge graph in a meaningful way. And then, a big problem that then happens when you bring all this data from different sources, which is how do you resolve the entities across sources, right? How do you figure out which entities are actually the same entities? And then finally, how do we then turn this into a knowledge graph and query it? Okay, so, right, the general problem I think we've seen here already, which is, we want to go from this sort of raw, messy, disconnected set of data that's hard to use into something that's well organized, that we can query, analyze, visualize, run machine learning algorithms on, and so on. Now, in the drug discovery problem, we worked on this for a while. We were looking at different combinations of sources, including things like materials, suppliers, markets, and products. And the challenge here was, the usual challenge, which is how do you bring all this data together in some kind of uniform framework where you can support the analysis that you want to do on the data. So the same thing happens on finding critical minerals. So this is a more recent problem we've been working on. This is funded through work of the U.S. Geological Survey, where, the U.S. government's interested in sort of how we can accelerate the transition to the green economy. And one of the big problems is how do you find these minerals that are sort of desperately needed for things like batteries and stuff. So these are things like lithium, cobalt, nickel, tungsten, all the ones that are sort of critical for things like batteries, but are often in short supply. So they have a list of about 50 critical minerals, which are sort of prioritized by the government in terms of how we could actually locate new sources of these things. And so the challenge here is, the same as the challenge in other domains, which is how do we organize the information about the data for this? And in particular, we want to know, where have these minerals been found in the past, and so that you can use that to predict where you're going to look for these minerals in the future. Okay, so let me talk first about, I'm going to walk through the steps here. So first, we have to represent the domain. And I think most people here are familiar with sort of the semantic web stack and all this stuff, right? So you have some kind of domain ontology. This is a domain ontology for companies, but it involves classes and properties and the relationships between them. In this particular domain, what we have is at the top level is what's called a mineral site. So this is something that is a place where minerals have been found in the past. Now this could just be somewhere where someone drilled a hole and then measured what they found there, or it could actually be a mineral site, could also be a mine. And a mine has a lot more information associated with it because someone spent a lot of money to actually, locate the mine, sample all the data. Maybe it's been in operation for many years, in which case they have a lot of data in terms of extracting from the mine. But in general, the top level that we're interested in here are sort of mineral sites. And then you have things associated with these things. The location is critical because you want to know where these things are actually located. But another really critical aspect is what's called the deposit type. So for any given mine, let's say that you have a nickel mine, then there's a set of different sort of deposit types for nickels. And that's important in this domain because different deposit types are often associated with different quantities in terms of how much of a material you'll find and what the grade of the material is there. So that's important. And then the other important part here is the mineral inventory, which is this is the information about what's actually been found, if it's an actual mine, what's actually been found in that mine. And there's different categorizations to this, and I won't bore you with the details, except to say that the typical kinds of information they want about the mineral inventory is how much material they found and what the grade of that material was. And then they can use that for doing other things like making predictions about future mines. And then associated with the mineral inventory, of course, you have documents because there's some source information. A lot of this stuff is going to come from documents, and so you want to record where the information came from. And the other thing that's associated with commodities and other details. Okay, so in general, once we have sort of some knowledge graph, then there's always the sort of what's called the serialization of the knowledge graph, right? So, and the point of this slide really just to emphasize the point, which is that different applications can have different ways that you want to represent the information. So in this particular domain, we are actually using RDF. We use a standard triple store. We use Jenna here. We use Sparkle type queries. But other kinds of applications that we've developed in the past might use other kinds of representations. So for example, the second one here is sort of key value or document stores. This is actually important if you have some applications where you have very large amounts of data, and maybe the data is sort of more monotonic. So we did an application previously, which was on combating human trafficking, where we pulled in lots of different data for lots of different websites. And it was pretty much a monotonic application in the sense that we only just added more data to the knowledge graph. There was never any sort of updates to it. But the information was huge, so it was on the order of billions of triples in terms of the data in the knowledge graph. And what we found for querying in that domain, it worked better to store it in sort of just a standard document store. We used Elasticsearch, which is a highly scalable document store. And it's just a different representation of the data. And so the only main point of this slide is simply that, well, for any given application, you may choose a particular one, but once you have some semantic representation, you can map it to any of these. Likewise, I've heard people in this meeting talk about things like Neo4j, which is a graph database, another representation of the data. So for this particular application, for the critical minerals, we'll focus on sort of the standard semantic web stack with RDF and Sparkle. Now, in this particular application, we bring in data from really 4 different sources here. The first source is sort of academic papers. So this often has detailed analysis of different kinds of minerals and things like the related deposit types and that kind of associated information. Second one is the reports from mines. And you think, well, why would these mines write reports that would be very detailed? And it turns out that mines are extremely expensive to build. And so they often need to bring in outside investors. And to do that, they're often traded on stock exchanges. And so in particular, the Canadian Stock Exchange has this nice property, which they have a standard that mines have to publish their data in. So, and many of the publicly traded mines also end up on the Canadian Stock Exchange. So it ends up as sort of the de facto standard for mining reports, which is kind of nice because it actually lays out all the sections in the reports and what information they have to present and how they have to do it and stuff. So the mining reports tend to be a huge source of information and an extremely valuable one because you get data from across the world, essentially, that's in these reports. But not all data is there, because some mines are privately held, and so they wouldn't necessarily publish the same report. But they might have their own reports of the information. Then we have data tables. These turn out to be an incredibly rich source of information, because what happens here is that people write papers about a particular commodity, and then they do a very detailed assessment of that commodity, compiling a tremendous amount of information from all kinds of sources across the world. And then they put together these really, really complicated tables that are hard to understand, which is unfortunate, but an important, but a really great source of information if you can sort of decode the tables. And I'll talk about how we do that. And then the last one is sort of databases. And so it turns out that there's the US Geological Survey, and then it turns out in the US, each state often has its own geological survey, so that we have some redundancy here. And they have their own databases and their own information stuff. And so there are a lot of databases. The USGS alone, produces dozens of different databases just on this topic. And so then the problem is you have to bring in all that data and try to make sense of it with respect to all the other information. Okay, so let me talk then. I'm going to go through some of the technical pieces here that we've done in this work. So first is, extracting the data from the papers and the reports. So as I mentioned, right, so these are sort of detailed reports that come from the mines themselves. So these are just a couple examples of the reports. And often these reports are enormous. They're on the order anywhere from a couple hundred pages to 600 pages. I've seen some that are like 1,000 pages. They're very long. And as the mine operates longer and longer, the reports get longer and longer. And so the real challenge is we only need a few pieces of information from these reports, but finding that information, can be challenging, and turning it into a structured format. And one of the things I've done over the years is built lots of knowledge graphs of different technologies that are out there. And one of the things that's, really changed in the last few years is the availability of sort of the large language models to do the extraction. So I would say that, in contrast to the previous technologies, things like Spacey and stuff that were out there previously, I think most people have seen the talks in this meeting, which is that really it's a tremendously impressive technology for extraction from textual information. So we've been using GPT-4 for the work we're doing here. But I think, many of these you could plug in. GPT-4 is not one of the open ones, right? There's some open source ones that are now available that we're starting to evaluate. But I think they all have these limitations that you have to keep in mind for whatever application you're building here. In particular, they don't actually understand the documents. It seems like they do, because they're often giving you impressive answers and such. But they really are just doing sort of word prediction. And so it's important to keep that in mind in terms of, the answers they give you, because they also have a tendency to make stuff up. If they can't find the answer to what you're looking for, sometimes it'll make it up. So you have to be careful about how you use these. So in this particular case, I'll show you an example. So we want to extract information about what are called resources, and there's different properties about resources. There's inferred, indicated, measured, and this has to do with how certain they are in terms of what's actually there under the ground, and this usually has to do with how they've sampled the ground and stuff. So I can give GPT-4 a query like this, right, where I say, okay, extract the total amount of indicated and inferred resources and corresponding grades from the following paragraph, and I just copy this paragraph out of the report, where I've actually gone and found the right paragraph in this 600-page report, right? And so this paragraph, I don't know if you can read it, but I'll just read it to you. It says, Table 1413 shows a summary of the results of the resource estimate of this mine, and at this particular percentage cutoff selected, the total indicated resources estimated at some number here with a particular grade, and it goes on to give the details about the inferred, indicated stuff. And so I think it's really quite impressive that then, it can take that paragraph, come back and sort of say, okay, here's the total for the indicated, which is the first value asked for, and here's the total and the corresponding grade. So it can actually figure out the right association and then pull out the total amount for the inferred as well. But this is great, but I gave it the paragraph, right? And so what really we want to do is actually give it the full report. And so now if we try that, so we can actually take this entire report, and in GPT-4, you, as opposed to 3.5, you can just drag the report into the system, and then ask the same question, right? So I asked the same question here, and sure enough, it finds the answer directly from the report, which is great. But it's great when it works, right? And so and the challenge here is that when these reports get very complicated, what you find is there's multiple tables. Sometimes some of these reports have the tables for the current year, and then they have the tables from all of the previous years, right? And so it gets a little complicated to make sure that the system is actually finding the right data from the individual reports and stuff. To give you a sense of sort of the complication here is, this is what they refer to now as prompt engineering. And if you haven't heard about prompt engineering, and turns out that this is actually a career. Companies are paying, very large salaries if you want to become a prompt engineer. Right now, I understand the starting salaries are around $300,000. So it's a very good place to be, but it's complicated, right? So once you get into not just one report where it works nicely, where you need to do this consistently across hundreds or thousands of these reports. I'll read this in case you can't see it, right? So the first prompt says, go through the document, find all the tables that give the mineral resource estimates or mineral reserve estimates. If there are multiple resource reserve tables, pull the tables that are closest to the doc date, which is a variable in this, which is, I assume that's because, well, the ones that are earlier in the document tend to be the current ones, right? So you want to find the earlier ones. Avoid any resource sensitivity tables, because this is a certain kind of table that shows up in the documents that don't have the kind of data that you want, but they're labeled usually that way. And if you haven't tried to use these systems and get the references, where you tell it the page number, it gets confused about page numbers. Right, so then you have to give it the algorithm for how it should actually give you a page number, right? So include the page number for the document that you got the table from. The page number can be calculated by counting from the first page to the page the table is found. I mean, so basic information that. And then you can tell it how to structure the information, right? So I can say return the list of tables as this JSON structure and give this structure and stuff. So you can see here, it takes some work to actually get the systems to do this, but it works pretty well once you figure out the right sort of queries and deal with all the sort of the edge cases and stuff. There's a second example here, from the list of, so now I have the tables, right? Now I have to pull the information out of the tables itself. So what really happens when you're doing this extraction is that you're usually giving it a series of queries to sort of make sure that it's actually first extracting the right tables, then from the tables, then you tell it how to extract information, right? So the second query, the second prompt says, from this list of tables, return the JSON structure that contains the list of categories found in the tables, the allotted categories, and here we give it all the different categories that it typically can find in these tables, and then return the value in this other format here. Right? So you can see that it takes some effort to do the engineering, but once you do it, then it works pretty well in terms of actually getting the documents and processing. Now that's not 100%. So in the projects that we're working on, one of the things we're doing is working with some of the domain experts and stuff to then create sort of tools where they can see the data, review it, and then sort of confirm that, yeah, this is the right information, which is why we needed to find the page numbers, because we'll have ultimately a tool that will extract the information but then show it to the experts so they can see, oh, here's the information we extracted, here's where it came from in the document, and they can see the page and the location of the page, and it can be highlighted, and they can quickly use their expertise to sort of say, yeah, that makes sense. The final result from all of this looks something like this, where we actually turn it into, first we turn it into sort of a JSON format, and then we import this JSON format and convert that into RDF, going through some, we have a bunch of checks to make sure it's in the right format and generate all the URIs and that stuff. But you can see here that the final set of information includes sort of the core information that you need, which is, oh, where did it come from? What's the name of the paper that it came from? What's the location, and so on. And then it gets down into the details for the mineral inventory, right? So at the top level, it's the mineral site I showed you in the ontology. Then we have the mineral inventory, which then breaks down the commodities and the amount that it measured for this mine stuff. And what you get out of this are, from each report, you're going to get tens or hundreds of sort of mineral site pieces of information, and then across this, for a given commodity, you might have hundreds of different reports that then you're doing the extraction from. Okay, so that's how we, in this application, how we do the extraction from the documents. But I think the same kind of techniques apply in lots of different domains here. Now the next piece of this also turns out to be really important in this domain, which is bringing the information in from tables of data. And as I mentioned, here's an example. So here's a paper by some researchers in this domain where they wrote, they basically write an entire paper about, okay, where are the world's resources for zinc or lead zinc? Okay, and then what they do is, as part of this, they publish. As part of the publication, they provided a data table, and you can download this data table. And this contains basically every known mine in the world that has actually ever extracted lead or zinc, and their estimates for how much material is actually available in those locations and stuff. The thing that's really quite complicated, and it's a little hard to see on this, which is that when you get over here into the details, it actually lists a whole variety of commodities, and then has a whole variety of, for each of the individual commodities, what the grades are. And then for each one of these, the grades are often represented in these sort of complicated ways, right? They have different kinds of units. They don't do things like we would expect, where they just say, okay, here's the grade in percent for this particular commodity. Instead, they do funny things like saying, well, if this is nickel, will tell you what the grade is in terms of copper, and they give you some mapping to copper, and then you have to do complicated things like look up, well, what was they do it in terms of the price of copper, because they're often interested in the value of these things, and then you have to look up the price of copper at the time that report was actually made to figure out how to do the conversion. But okay, so how do we take a table like this and map this table? So we've been developing some tools over the years for doing automatic sort of table understanding. So the current tool we have now is called SAND. And this is essentially a general tool for essentially trying to learn and then show the user the mappings for the tables. And one of the nice things about this tool is that it actually can take in a number of different semantic modeling algorithms. The one that one of my PhD students is building now is called GRAMS. And he actually built, this general tool called SAND. And the general approach that we've been taking here is to sort of say, well, there's a lot of data that you may already know. One of the things that's really hard about mapping tables is that it's really hard for for people to do it, right? It's a really tedious, sort of complicated task, and it's hard to get the mappings right. So our goal is to essentially help the user as much as possible. In the cases where you can't completely automate it, then you show the user the visualization of the table, and then they can refine the mapping. But what this slide shows here is there's a table here at the bottom. It gets loaded into Sand. And then the idea is to actually look to see if there's other sources of information that are out there that we can use to help figure out the mapping of the table. So one knowledge graph, you could actually plug in any knowledge graph you want. So you might have your own knowledge graph of a particular domain that you want to use here. But one knowledge graph that's quite general that we use is Wikidata. If you haven't used Wikidata, it's sort of I would think of it as sort of a structured form of Wikipedia, right? So Wikipedia has all this information about the world. Wikidata also has all this information in the world in a structured format, right? In sort of a Wikidata ontology, which is kind of messy because it's kind of crowdsourced and built sort of bottom up, and so it has a lot of sort of redundancy in it and stuff, but it's still a very useful model because instead of just having a table of data where you don't know what it means, there is an attempt to actually map all the data in Wikidata to some domain ontology. So both of those things are input, and then you have whatever your semantic algorithm, modeling algorithm is. This is sort of a competing algorithm, the MTAB, but we use grams in this work. And so the idea is that you load the data into the system, and then what we do is the bottom figure here shows the table loaded into Sand with some options that you can select. And the top shows essentially the semantic model, the semantic description of the table, where it's essentially taken this table and mapped it to the domain ontology that we're using here. So the way this works then is for this particular application, we would bring in some table that maybe comes from one of those papers or from one of the mining reports and load that in. And then you have sort of the mineral knowledge graph that we've built so far, right? So we're in the process of sort of creating this very comprehensive mineral knowledge graph with all this data. And then the idea is that the system then uses the sort of the background knowledge in the table to essentially come up with a proposed model that it can show the user. So let me just walk through a few steps in terms of how that actually works in practice. And I'll show it on a different domain because that's what I have on my slides. So here's a domain from a Wikipedia table about political offices in Austria. And so what we're trying to do is come up with a model that looks like this, which sort of says, all right, this table represents what are called third presidents in Austria. I guess they have, it's sort of like presidents, vice presidents, and then I guess the next step would be the third president. And it contains information about, the political parties, when they entered office, when they left office. And so the challenge is, given a table like this, how do you figure out what this table actually represents, right? And so this is a table from Wikipedia, so you don't know the model a priori. So what happens here then is to essentially use information about entities that are already in the knowledge graph to help you figure out the model of this new entity. So in this case, and the reason we do this is to minimize the need for training data, right? So we built an earlier tool called Karma that would sort of also try to help the user automatically create these models. But the problem or challenge in Karma was the fact that you needed a lot of training data before it really became useful, right? It needed to see lots of examples. And so what we've been trying to do in this system is to try to minimize the amount of training data that you need up front by using existing sources that are already out there, or maybe you have in your own knowledge graph. So here we have the table that comes from Wikipedia. On the right there, we have the corresponding information if you look up these people in Wikidata. Now, this assumes, right, that there's some overlap, right? So the key idea here is to look for information of things that you already know something about. And it doesn't have to be that you have complete overlap. All you need is a few rows of data that there's some overlap, and then you can use it to propose a model. And the most recent work that we're doing on this doesn't assume any overlap at all. And it does that by essentially taking sort of background knowledge. It does assume that you know something about the domain and you have some data for the domain, and then you can essentially learn what different parts of the domain actually look like and then recognize them automatically. But in this work, in this slide I'm showing you here, there is some overlap. And so it turns out that, you can look up this particular person, Eva, they also show up in Wikidata, and you can look at sort of the relationships, right? So there's some information in this table over here. Notice that the same information sort of appears over there in a slightly different format, but it's still more or less the same information, right? And so you can sort of recognize that there's some mapping between the 2006 and the start time over there in the Wikidata version of this, which is October 30th, 2006, and then the corresponding end date. and you do, and likewise, there's some mapping here between the parties and stuff. And so then you could basically propose a potential mapping. And so what Grams does is essentially starts with this table, and there's the Wikidata, which is the knowledge graph that's using here. The contextual values, this is just sort of the contextual information where the table appears, because it turns out that for a lot of tables, what happens is some of the key information is often in the caption, or it's in the title where the page appears and stuff. And so you sort of want that information as well, because you can use that to sort of bias the candidate knowledge graph. And so what happens then is you take this table and you build this, what we call a candidate graph. So the candidate graph sort of says, okay, based on all the examples we see, here's the possible set of mappings to the domain ontology that are sort of consistent with the data that we see. But that doesn't mean that those are all right. I mean, some of them actually could be misled by some other data. And then what it does is it goes through a reasoning process where it sort of says, okay, well, I'm looking for sort of one consistent set of mapping across all these possible mappings for the individual things. And so then it proposes the final sort of semantic description, which is, in this case, the correct model of the table. Okay, so, and this, I mean, this, of course, very much, how well this works very much depends on the particular table, how much information is in the domain. But for a lot of domains, there's a lot of repetition. There's a lot of information that you see over and over again. So for in the critical mineral domain, you see things over and over again, like, mining site names. You even get, the deposit types, even some of the values occur because the information occurs in multiple places, right? The table that I showed you from that paper is a compilation of data from lots of different places. And so you may see the same data coming from other sources as well. So there's some overlap in the data. So you can use that, and this is sort of an evaluation. I won't go into all the details of the evaluation except to say that we evaluated on two things. One was a set of syntactic tables from a semantic web competition that happened at ISWC. We found that those were actually relatively easy and simple because they made certain assumptions in the synthetic data. So then we took a set of real-world tables. So this is 250 real-world tables that were sort of selected from across different domains, and then compared all the sort of competing approaches out there. So Grams ST is a simpler version of the general version of Grams using what are called Steiner trees, and then Grams. And the bold is sort of the system that performed the best. So you can see that Grams generally outperforms or performs about the same as the other competing systems there. The two columns, CPA and CTA task has to do with doing what's called sometimes semantic typing, identifying the particular class of information. And then CPA is the properties. So can it recognize the right properties? Because remember, we're not trying to just identify what the class of information is. We're trying to understand the full sort of relationship between all the classes and come up with all the links between them, which is a more challenging problem. Okay, so that's Grams. So if we take the table that I showed you from that paper, here's sort of one automatic table that it actually builds from this. And it requires some refinement in SAND, so I won't claim that it does it right the first time, but it actually gets a fair amount of the table right. So it identifies sort of what the corresponding information is to the mineral site and then gets into the mineral inventory. So that's the final model. But then once SAND has this sort of model, then you can just ask it to generate the RDF, right? So it'll just take the table as input and then produce the RDF version of it. And I should have mentioned on the first slide on SAND, I have the link to SAND. So SAND is open source. It's in a GitHub repository, and I believe my slides are on the download. But you can also just search for SAND at ISI. I think you'll find the GitHub repository for this. Okay, so now let me talk about how we actually resolve entities across sources. Because one of the problems now is that we've brought information from a variety of places. So I mentioned that we have these databases. I haven't talked much about the databases yet, but we've been studying a couple of different commodities. One is tungsten, where across these different databases, there's about 8,000 records. So you can see that there's a lot of sort of potential mines for these commodities. And for nickel, there's almost 3,000 records. And for nickel, for example, we have MRDS, which is a USGS database of sort of occurrences of different minerals. USMIN, which is a more recent USGS database. So at some point in the 80s, I think they stopped populating MRDS, and then they switched over to a new database. But of course, there's information spread across both of these that you care about. And in this case, cobalt and nickel are often found closely together, and so in this case, you query for cobalt. And then there's the information you extracted from the mining reports, right? So I showed you before how we get the information out of those reports. But when we get the information out of the reports, we don't actually know which mine that corresponds to that's in these corresponding databases, right? So it's a matter of figuring out that, okay, how does this information relate to these two other databases? And then we have the mineral site data that comes from sand, right? And again, there's just some reference in the table. If I go back here, there's some name and there's some country this is in. And so now it's a matter of figuring out, well, which ones of these are the same. So this is a common problem across lots of domains. So what do we do here? So the first thing is we look for some common information that pretty much always shows up in all of these sources, right? So in particular, we want to identify the site name, all the name aliases, because it turns out that for each one of these mines, what happens is that many of these mines run for many years. They get bought by another company. The company decides to change the name of the mine because it's a new company. And so you have this, not only do you have a site name, but you might have various site aliases in terms of how this has been called over time. And you always have the commodity. In the mineral world, everything's about a particular commodity. And so, and in fact, it's interesting because most mining companies specialize in a particular commodity or some set of commodities that are usually found closely together. And that's all they care about. So one of the interesting problems that USGS really cares about is finding all of the other commodities that they may have ignored but maybe mentioned in their reports, because it turns out that if you're a company that does copper mining, that you only care about the copper mining, you don't care about all the other minerals that maybe you found along the way. Those are just sort of discarded. In fact, there's a whole industry in actually remining sort of the tailings of mines, because it often contains all these other minerals that they didn't actually care about when they mined it. But maybe they weren't actually that valuable when the company was mining it. Maybe they were and they just ignored it. And now they go back and they actually reprocess all the tailings to find some other commodity out. So in this case, what happens here? We have these attribute descriptions that are often in the database descriptions and so on. And so we can use these to basically say, okay, this is commodities available at the mineral site might be the language that's used to define one thing. And then we have to classify this, right? Does this correspond to the name, the site name, other names, or the commodity? So we can do this for sort of the general things that are sort of in every source and figure out, where do we get this information? But then we still have this problem of, okay, how do we tell which of these, in this case, which of these mines actually correspond to the same location or the same entity? Really, we're talking about the entities here. And in sort of the entity linking world or entity resolution world, there's usually two steps, because one of the things that you find is that, well, if I say, all right, I want to figure out which two entities are the same, and I've got, 10,000 entities I'm comparing, you don't really want to do, 10,000 squared comparisons, right? Because that's just too slow. So usually there's a first step, which is, all right, some kind of what's called blocking, which is how do I generate a set of candidate entities that I want to then look at more carefully to see if they're the same. In this particular case, the way we do blocking is by looking at the location, because the location gives you some pretty good information about where, which things are likely to be the same. And usually there's some kind of threshold. So this could be, in this case, empirically determined that maybe we decide that, okay, 50 meters is, how close we want to consider. I don't know if 50 meters is the right number there, but and those that are then within that distance would be the ones that you would actually want to compare and do sort of further analysis to decide if they're the same. But I want to emphasize here, maybe you have a domain that's not spatial, and so you don't want to do blocking based on the location. You can do blocking based on, if it's people, you can do it based on last name. Other domains, you might do it on some other attributes that would likely be common across the entities that you want to compare. So in this particular example, the color represents the unique mineral site, right? So it turns out that Ivanhoe and Brown Lake are actually the same mine. but they were renamed at some point, right? And so you have to look at more than just the name to figure that out. So, okay, so what do we do? Once we generate the candidate entities, then we use some embeddings, which are really quite useful for this kind of task. So we can essentially take the common sort of set of attributes and look at all of the other attributes associated with it. So in terms of a database like MRDS, there's probably like 100 different attributes that are associated with each mine. And so all of this information gives you a little bit more information about it. And instead of trying to sort of tease apart exactly which attributes to use, one of the techniques that people use nowadays is sort of say, okay, well, I'm going to basically create an embedding for all the information that is associated with each of these entities. And then I can compare the embeddings, right? Because the embeddings basically give you a vector representation. And so you can see here, this is sort of the vector representation for each of these different mines. And then I could say, well, the ones that are closer together are going to be more likely to be actually the same mine, right? So it might decide that, okay, Ivanhoe and Browns Lake, this case, are closer together, they're farther away from this other one, and so you may decide it's the same. And and if it turned out that this was really important in terms of your final task, then you might have a user sort of review the data. In general, for this application, it turns out that, well, if we actually combine some mines that are close together but are actually different mines, it doesn't actually really matter for what we're trying to do with the data, which is to understand for this deposit at this location, what's the total amount of material that's there. But in some other applications, you might want to get this exactly right. Okay, and then here's just a graph sort of showing an example, which is, okay, these two mines, when you put them on a map, you can see that not only are they close together, but they also have similar embeddings, and so you end up deciding to group those together. Okay, so that's that's sort of the step in terms of how we do the entity resolution, how we actually combine the entities together. Then we have to actually turn this into a knowledge graph. So what do we do here? Okay, so essentially I've described how each of these sources is sort of mapped to the ontology, right? So as you're all familiar with, we can use a triple representation here to represent all the data. The LLMs basically extract the data into this sort of JSON representation, and then we have a simple script. It's actually a feature in that's part of SAND that we can then take in JSON and then automatically convert it into triples. The SAND itself, when it imports a table and builds that model of the table, can then just output all of those into triples. For the databases, we have a system called Karma, which I mentioned before, which is also available as open source, where you can use that for mapping, sort of more manual kinds of mapping of a database or a table into a domain description, which then again you can use to convert all that into triples. And so you create all those triples from all these different sources. All of that gets loaded into a triple store. So in this case, we're using Apache Jenna. The reconciled entities, so the entities that I just described in terms of how we reconcile those basically get inserted as what are called same as links. So this is just a link that between two entities where we say, okay, these are basically the same thing. I mean, the semantics of same as get confused sometimes, but in this case, we really are trying to assert that these actually correspond to the same mine or mining location. And then the resulting knowledge graph is then queried in Sparkle. So we essentially are using Sparkle to do all the querying. So the final knowledge graph gets, we create this critical mineral knowledge graph, and then we can do a query that sort of says, okay, for all the mines of a particular commodity type, give me the tonnage and grade, and then we can use that to then build what's called a grade and tonnage model, which is shown on the right there, which oftentimes the geologists are really interested in this, which is they're looking at the relationship between, for all of the mines of this given deposit, commodity and deposit type, how does the grade relate to the tonnage here? And this is important because what they're really trying to figure out here is, well, if I found another mine of this commodity and of this deposit type, how much material and what grade would I expect to actually find? And it's going to be, somewhere in the middle here, right? So that they could then estimate whether or not it would be worth looking for a mine of that type. We had a hackathon 2 weeks ago where we got together and actually built from scratch the mineral assessment for nickel. And this was the result there. So this was actually built in just a few days, where USGS would typically take 2 years to do the same kind of assessment. Not just this step that I'm talking about, but the full assessment where they're trying to figure out, okay, what are the most likely places they're going to actually find a mine? And for a single commodity, that would typically take about 2 years to do that. So I'm not saying we haven't completed it in a week, but that's the goal for this larger program that we're in. The other piece of what comes out of the knowledge graph now is what are called essentially the list of all the mines of a particular deposit type. And this is important because not only do I want to estimate the amount of material that I would find in a location, but I want to actually essentially put these on a map so that then I can train a system so it can sort of see where are likely locations to look for this type of information, right? So this shows this is all for nickel. It shows all the different deposit types for nickel, which are then color-coded here. And let's say that I'm looking for, in this case, they're looking for a deposit of any one of these types because these are all a very similar kind of type of nickel. And then what they do in the next phase is to actually load this into a system where they can train the system with positive and negative examples, which then gives it an idea of where to actually look for these things in the future. Okay, so that brings me to the discussion, which I'm about on time. So one question you might ask is, well, why do we even need a knowledge graph when we have these nice large language models, right? Can't we just load all the data into the large language models and be done with it? We can just ask the questions and stuff. The challenge here is that, well, that might work well. I mean, there's some, for Q&A kinds of things, if you want to ask for simple kinds of questions, there's some problems in some domains that actually might work reasonably well. But it's not going to work well when you have sort of much more complicated kinds of analysis that you want to do on the data. And I think trying to come up with the total, the prediction on the amount of material that you're going to find is an example of this, where it requires sort of a combination of the information that comes from these reports and putting it together. And I'll give you an example here, which is that we load in the mining reports for a given mine every year. And one of the queries that you end up having to do here is to say, well, when I go to create the final result for this mine, what I actually have to do is query across all of the different years that this mine was in production, add up the amount of information that was extracted each year, and then add that to the total amount of predicted material that's actually still in the ground. And that becomes the amount of information, the amount of material that I think this mine in sort of its original state had. Right, so there was sort of like when it was first before anyone started to remove any material, that's how much material they think was actually in the ground there. So that's a fairly complicated assessment that you have to do here, and then you may not want to depend on the system to do that assessment completely right, even if it could. That you want something that's explainable, right? So you need something that you can go back to the expert who understands the domain and could actually look at it and review the data to make sure that, okay, the information that's coming out is correct. So one issue here is that, well, when you're doing sort of complicated analyses, that I think the large language models are going to fall short. And then, especially if you want them to explain the reasoning. Now, they can do explanations. We've seen nice examples do explanations, but they can't always fully justify the results. And so that's another issue. And then finally, you want to be able to curate the results. And so in this case, you want to be able to curate the intermediate results so that you have some confidence that the final results are actually there. Okay, and then in terms of where we've used AI in terms of the role in building the knowledge graphs here, there's a number of sort of interesting places that are important here. One is clearly just the underlying knowledge representation, right? So we have the model of actually what a mine or a mining site looks like and all the different associated pieces of it that you actually care about. So that's a key piece in terms of representing that information. Then we have the large language models that are really nice for extracting the information from the text. So getting the information out of the text that you want to use for building the knowledge graph. Get the information out of the tables, right? So we're exploiting this idea of using existing knowledge graphs to essentially learn a model of a new source. So this is sort of a bootstrapping thing where, once you have some knowledge graph here, you can really exploit it to be able to rapidly bring in new source of information and build the model of those that's sort of consistent with all the other previous data. And then finally, when we're going to do the entity resolution, right, the use of embeddings is actually really helpful here. So it actually solves a problem that in earlier work that I've done in terms of entity resolution, where you'd spend a long time trying to decide which attributes to pay attention to and how much weight to put on each of the attributes and stuff. And now that's actually much easier because you can sort of use these nice techniques for creating embeddings and comparing the different vectors and stuff. So those are just some of the techniques that I think are particularly relevant and interesting here in terms of being able to create knowledge graphs for new domains. Now, I want to give credit to the rest of the team here since I didn't do all this work myself. So there's actually, a number of my students here at USC, and then we're collaborating with University of Minnesota and a small company, Infralink, that are also working on different pieces of this problem. And then our sponsors here are, US Geological Survey, which is sort of leading this, and then the funding is coming from DARPA, which is the large funding agency in the U.S. that funds various things. And this is important for the U.S. because they sort of view this as kind of a critical problem. I mean, not just for sort of building the green economy, but making sure that the U.S. doesn't get into a position where it's depending on other countries that maybe don't want to share some of the minerals with them and stuff. And so they view this as a particularly important problem. So that's it. I can open up for questions.
And by the way, there have been a few papers comparing the drug discovery process and the mining process.
Oh, there have, okay.
Yeah, because it's decreasing utility. I mean,
yeah.
The more you dig, the less you find, right? That
yes.
is a kind of,
Oh, interesting.
Anyway, questions?
Thanks really for this super nice talk that covered a lot of different tactics, let's say, to extract information out of various sources. I think one of the points that I'd like you to elaborate a bit on is that we always seem to compare these language models or some form of automation to a higher standard than we expect of people.
Mm-hmm.
And it's sort of an unfair comparison in some sense, right? Because if we can at least do as well as what people do, then it's already a very useful thing. If we do not even as close as what people do, then we still need people in the loop.
Yeah.
On the other hand, if we do things that people don't want to do, then that's even better, right?
Yeah.
So maybe you can reflect a little bit about that with respect to your interactions with the users, and how do we deal with the expectation alignment about what these technologies can do for users?
Mm-hmm. Yeah, I think it's a really interesting point, because one of the geologists that we worked on this project actually wrote one of those papers there. They compiled all that information on nickel. He's working with us on this project. He characterized that task of compiling all of this data as a soul-crushing exercise. Right? So, and I think he basically assigns it to his students. He probably doesn't do it himself. So it's a really hard task, right? And so I think there is an opportunity to automate some of these tasks that are extremely painful. And so I think the challenge is that it doesn't always get it right? And so an expert, when they're looking at these kind of reports and stuff, they have enough background knowledge that they can sort of look at these different kinds of reports and do an assessment to understand that, oh, okay, this is actually what the table is telling me versus something else, right? So the tools are really useful because you can automate a lot of these things, but then the problem comes up that you don't always have the same level of background and expertise to actually essentially do the extraction correctly.
Yeah, that may very well be the case, but again, we know this when we try to do, say, crowdsourcing for ontology construction, or the inter-annotator agreements tend not to be anywhere near what we would want them to be.
No, it's a great point.
Right? And that's kind of what I'm getting at, is even if you have experts and you ask them to give the same task, they will miss things. They will incorrectly transcribe things. And you need an estimate of the human error in order to correctly, I think, assess the performance of the machine.
Yeah.
Right? We always do these benchmarks. When you know all the answers, here's the maximum you can do. But the task is actually, can you do it as well as what people do? And sometimes we don't have good estimates of that.
Yeah, no, it's a really interesting point. It would be worthwhile in this domain to actually measure how the people that do and how
because I guess it's a really different human perspective, like a human-centric perspective about the application of technology in the workplace.
Yeah.
right? We're not just doing computer science now. We're really asking the question, how does this help people? And we need we need to promote a realistic worldview about the utility of these technologies in practice.
Yeah.
Yeah.
Yeah, I mean, I hope I didn't give the impression that this is not useful for this task, because it's incredibly useful for this task. It's just that it's still one of these tasks where in working with sort of some of the experts at USGS, they really, really care about getting the data right. So it's important to them that they don't just extract some numbers and it's like, oh, it's right most of the time. I think one of the challenges when using these things is how to get to that level of accuracy that ultimately they expect in the system, right? Previously it was done by a person. They were getting fairly accurate results, probably not perfect, but pretty high accurate results. And so then the challenge is, well, how do you get the systems to get to the sort of the same level of sort of performance that, and I think, there's lots of room for improvement, but I think that they're getting better all the time. So we'll get there.
So to Michelle's point, maybe we need to ratchet down our gold standard to be a bronze standard or something like that. So when you were talking about the import of structured data into your knowledge graph, it sounded like you had some clever embeddings that where you were using AI to figure out to take fresh data, like fresh structures, and say, "Oh, I recognize that, and I know how to interpret this structured data." Is that correct?
Yeah. So what it's doing is it's using the fact that the information in Wikidata has already been mapped to a domain ontology. So in a lot of knowledge graphs, if you have an existing knowledge graph, then the assumption is that you've already modeled the data that's in the knowledge graph. If you have a knowledge graph that has no representation, it's not helpful. But it has some representation of the data. And so then the idea is that you're looking at this other data and sort of saying, oh, I think these entities map to this corresponding entity here. And look, I have the similar kinds of data, and I can look where that data exists here. And then I can look at the relationships in the existing knowledge graph to sort of say, oh, I'm going to hypothesize that the relationships in the existing knowledge graph are the same for this new data. Right? And it's essentially proposing those as possible relationships. And then it's doing some final assessment on those. And then showing them to the user, because part of the challenge here, and we learned this in sort of previous tools we built, is that you don't always get it right. And so what you want is a tool that sort of allows the user to sort of visualize what the system has come up with and then make corrections, right? Interactively sort of be able to work with the system, say, oh, no, that's not quite right. Here's actually the correct mapping. So then the final result is correct.
Got it. And then one other question, how much of the fruits of your labor are sort of open source tools that we can profit from?
So all of the systems we build, we make open source. So we are making them available under the MIT license, which even gives companies the ability to use the tools. The only thing that license has is, I think, an attribution requirement. Right? So the MIT license has that you just have to give us credit for having done the work.
Any other questions?
You just mentioned that users can basically get feedback on this models. So are they also part of the training? So they would be also kind of learned for the next try?
Yeah.
Okay.
So what happens is essentially as you, at least for the respect to the table learning piece of it, as you expand the knowledge graph and you add more data in it, it's effectively understanding, it's seeing more data, and they become part of the sort of the data and model that it understands. And so then that data can be data that it uses in the future and stuff. So it's not actually adjusting the weights on the things, but it's essentially augmenting what it knows about the world, so that when it sees new information, it's more likely to find something that it could actually relate it to.
And also basically as a base, it shouldn't be necessarily Wikidata, or it is already trained on the Wikidata and you can feed any other graph as well, knowledge graph as well?
Yeah, you can put any knowledge graph you want into it.
Thank you.
So it's not assuming that there's a fixed one. It just happens to be that Wikidata is really nice because it's large and comprehensive and covers lots of different stuff. But you could have, I mean, in this case, as we develop our own sort of mineral knowledge graph, then we could just use that instead of the larger thing, because it's a very specific domain and all of our data is going to be about minerals.
Yeah, I was just wondering, I mean, thank you. It was a really, really interesting talk. And I enjoy the part about how you're having the iterative look by the users. I think that's something that we're trying to do as well. And I think it really helps to keep them in. And especially, I'm sure your community is similar to what I work with, which is the agricultural researchers. And the researchers community, they're very much concerned about the accuracy of things. But the question I had was like, you did say, and I can see that this would be appropriate for any kind of domain. Do you have any feedback or experience with people doing this in different domains? Has there been any, war stories about how it's gone, or any other issues? Because the mineral example seems, you have some really nice, very like these reports that are formatted very similarly and things that's not always the case in other.
Yeah, we've done a
domains.
lot of different domains. I learned different lessons in different domains. One that I think was particularly interesting was we did a large project where we were integrating data about art collections. So this is the part of what was called the American Art Collective, which is it. We worked with 13 American art museums where we were basically building a knowledge graph of all of their data about artwork. And what was interesting about that particular project, and one of the big lessons we learned there, was that in the art and sort of other related communities like architecture and stuff, they have this ontology called CDOC CRM, which is, many of you may have heard of it, but if not, it's just a really complicated ontology. I mean, and one of the things that happened in that project was that we spent a tremendous amount of time, in fact, I would say we got sort of bogged down in sort of this process of actually mapping the data to this really complicated ontology, as opposed to getting to the really interesting part of the project, which would, in my view, would have been, well, how do you, once you've done all this and you've integrated all this data, actually using it and building interesting applications on top of the data. And so my own personal lesson that I took from that project was you want you want to use, common ontologies, but you want the ontology that corresponds best to the kinds of problems that you want to solve, right? The kinds of things you're going to do. And so that was an example where the mapping process kind of, took on a life of its own, and it ended up consuming the project and stuff. But every project is a little bit different, and sort of one of the reasons I talked about sort of like the different serializations of the knowledge graphs and stuff, because we've used all of those different sort of ways of organizing the data, right? One of the things you always have to look at in a given problem is, well, what's the best way to sort of use the existing tools and infrastructure for that particular problem that you want to solve, right? Every problem is different.